A warm good evening to all the participants. I welcome you all to the fourth day of the Aital FDP titled Advanced Biomaterials and Tissue Engineering Applications. Before proceeding to the today's session, I would like to introduce Mr. Piyush Padmanabhan. Let me introduce. Piyush is a biotechnology graduate from VIT University, Vellore. Post his degree, Piyush pursued a sales and marketing role in the pharmaceutical sector, where he worked in the renal and liver transplantation segments for companies such as Biocon Limited and Roche Pharmaceuticals. During this phase, Piyush noticed an ever widening gap between the demand for transplantable organs and the availability of such organs. Many patients to this date wait on transplant wait list for long periods of time, not only in India but globally. With a goal to bridge this gap, Piyush co-founded Next Big Innovations Lab with Alok and Pooja. NBIL is a deep tech bioprinting company that builds Trivima bioprinters, envisioning modular bioprinting for diverse applications, and various other deep tech biofabrication projects aimed towards clinical applications. The 30-member interdisciplinary teams work on diverse projects with multiple collaborations, and Piyush currently heads these efforts as the CEO. Piyush currently holds three patents in the domain of 3D bioprinting, but strongly believes in deep collaborations for a sustainable and long-term clinical applications of bioprinting technology. With this brief introduction, I would like to hand over the platform to Piyush.
Thank
Thank
you
you.
so
Thank you
much.
for
Thank you so much, Dr. Jay, for the introduction. And thank you so much, Dr. Venkatesh, for inviting me to speak at this FTP program. With that, I'll just introduce, what I'm going to talk about today. Primarily, it's going to be bioprinting of bone. A little bit of the work that we have done in the space of bioprinting or 3D printing of bone. And I'm also going to explore a little bit, a very little bit about the other applications that bioprinting might have. I do have a section towards the end where I'm planning a Q&A and all of that. So we can have the questions then. And yeah, I'll just share my screen. Yes, sorry, I think the app suddenly quit on me. I'm just this one. I'm just going to share my screen. Just give me a minute. Yeah. Are you able to see my screen? Is it visible?
Yes, sir.
Yes, sir.
Yes.
So, I've sorry about the technical problem, but I just named my slide. I'm going to talk generally about the 3D printing and bioprinting of bone. So the primary application of bioprinting is far and wide. Now, what I'm going to talk about is about specifically on bone and how there are different technologies that can be used for applications in bone. So before that, I'll just quickly start off with who we are as a company. As such, we are a company that's focused on three branches. We are focused on technology, ecosystem, and partnerships. And the company's name is Next Big Innovation Labs. You can call us NBIL for short. The long-term vision is to see how we can apply these bioprinters for clinical applications. How this technology can actually change the lives of patients or the way the patients are being treated currently within our healthcare ecosystem. And that's with that ethos or that driving force for us. We partner and work with multiple people across industries, across academia, to build strong, solutions for bioprinting. So I'll just start off with our journey, what we have done over the past few years. In 2016, we started the company in Bangalore, India. We received our initial, support from Autodesk India. So we are one of their star companies. They promote us wherever they go, and they've done like a video on us, and they've covered our work extensively. And now Autodesk helped us, with the licenses that we had from Autodesk. We were able to actually build out the entire machine from the ground up. We were able to design these machines. So when we started out, we went we during our market research, we went to a lot of researchers who are working in the space of bioprinting and 3D printing, especially people who are working on bone, skin, and liver. And one of the major feedbacks that we got was that if you need to create a company that is specifically working on different bioprinting aspects, not only skin, you're looking at bone, you're looking at liver, you're looking at cornea, if you're looking at all of these aspects, you need to have complete control over your engineering. So what happened that year was that in 2016, once we did the market research, we knew that we had to build the technology from the ground up. We tied up with Autodesk that provided us with softwares for 3 years, free of cost, that allowed us to do our initial work, and a bit of funding from the central and state governments. So this bit of funding that we got from central and state governments actually allowed us to sort of build out the entire tech. We were able to build out you know the basic crux or the basic technology of 3D bioprinting. We were able to play with different pneumatic systems. We were able to work with different biomaterials. So we went back to these same researchers and we told them, you know what, we have this technology in house. We'd really like to test out the technology and we'd like you to give us some biomaterials to play around with. So that's what they exactly did. They gave us some biomaterials. We were able to validate the technology that we had. Once we had validated the entire technology, we knew that the next step that we had to take was doing something with the technology, and we started bioprinting human skin. The next couple of years, from 2018 to 2020, we were focused on bioprinting of human skin. And we also collaborated with companies like Merck to further validate the technology. We were one of the top startups, in the field under the Merck banner, And we received two technology patents that year, which allowed for precision in movement and precision in temperature control within the bioprinting system. So with that, 2020 COVID hit. We knew that everything, all our operations were shut. So we pivoted a little bit. We stopped the research that was happening in skin, and in 2020, we launched an entire course. We had 4 years of data from 2016 to 2020 about bioprinting. We tied up with different professors, and we created an entire course on bioprinting that allowed people to understand what exactly bioprinting was, what the applications of the technology were. And furthermore, we started investing more on building bioprinters that are customizable, that have different applications across industries and disciplines. So we partnered with High Media to see how we can provide these bioprinters at a much more effective price point to individuals across the country. And right now we have close to around 35 or 40 plus installations across the country, and we are currently expanding globally. We have our first installation that happened in South Korea, and next month we have an installation in the Middle East as well. So we've been lucky to be incubated also under the Karnataka state government as well as under the Atal Innovation Mission. So we've been able to work collaboratively with a lot of top institutes such as AIMS, IIT Hyderabad, and Manipal University. We have been ranked one of the top 100 companies to look out for in 2023 by the World Economic Forum as well. And currently are one of the companies that are there within their network, and we get to interact with a lot of people who are operating in the space of deep tech. So we consider ourselves to be a deep tech company because we work at the fringes of what bioprinting can possibly do. So, as I said, overall, we have around 30 right now team members, and when we are growing, we have a lot of collaborations, and we are open to collaboration. So, people who want to collaborate with us, please reach out, and we'd be happy to see if we can take the collaboration forward. And what we do, another thing that we do is we partner in such a way that the printer has to work for your research. So that is the goal with which we sort of work in this space. There's no point in putting a machine and it not working. So with that, I'll just quickly brush through. I'm sure the whole talk has been about 3D printing, bioprinting. So I'm just going to quickly brush through what the 3D bioprinting process looks like. You have cells, biomaterials, and nutrients that form the bioink. This bioink is deposited layer upon layer in order to form a three-dimensional structure. This three-dimensional structure is called a scaffold. These scaffolds are then incubated. These are with cells, right? So the cells are there within each one of these lines. And if you see, each one of these lines are really nicely printed. You're able to control the amount of spatial positioning of these cells per square millimeter of the scaffold. And over a period of time, when you start incubating the entire scaffold, you'll see the cells slowly start to metabolize the biomaterial. As they metabolize the biomaterial, they start forming their own matrix. They start forming their own ECM. And you will see that slowly transform from a grid-like scaffold into a beautiful thin skin-like structure. This takes about 1 to 2 weeks. This is the effective process of bioprinting. Why, how the process of bioprinting goes. For any company that is operating in the space of bioprinting, why bioprinting? The only answer is we are looking at this. This would take us about 15 to 20 years more for us to reach this stage. But meanwhile, we are trying to explore other applications through which bioprinting can actually affect the lives of patients. One is, we understand that bioprinting has precise spatial positioning of cells and enhanced cell to cell interactions. Because of this, we are able to create these multi-layered structures for tissues, be it bone, be it cartilage, be it liver, be it skin, be it the most simplest avascular organ to the most highly vascularized organ. You are able to create a simplified version of those within the lab, and you're able to create complex tissue architectures. This allows you to actually create these tissues at a larger scale. You're able to create it for applications such as medical device testing, where you can basically test different drugs, or you can test different medical devices on this. The second one is you also have an ability to test certain cosmetic products. We have ability to test certain chemical products on these bioprinted tissues. It allows you to explore the realm of cancer biology, where you're able to create specific tumor models, and these tumor models create a very beautiful structure in the lab for you to test different drugs. What we are exploring with different hospitals is to see how bioprinting can be used for something called personalized medicine, where we can utilize bioprinting in conjunction with microfluidics and other technology, specifically to build a more personalized therapy for cancer patients. Because generally right now what we do is we go with a more western data based approach, and what we believe is we need an Indian data based approach. That is specifically how we are working in this space. So I'll quickly go on to what are bioceramics. So now that I've given you like the base layer, let me build up on that. So bioceramic is a class of materials specifically that have that can be used for skeletal or musculoskeletal system. So you can use it for any form of skeletal repair. They have different properties. They can be a little bendable, they can be more rigid. It depends upon the kind of bioceramic that you're working with. There are different applications of bioceramics though. There are bioceramics that are there for orthopedic applications. There are bioceramics that are there as bone grafts. A lot of you would have heard that they make bone cement and they put the bone cement at very complex fractures, especially when you have cancers of the maxillofacial bone structure. In those areas, you actually have bone cement that is specifically used over there to fill up those gaps. You have bone grafts that are taken from the patient itself. Even in dental implants, generally they take a portion and they start churning it inside so that you get a pulp, and that pulp is what holds your new tooth together. So you have different ways in which bioceramics are explored. Some of them are naturally from the body and some of them are external. But what we are going to focus are on the external bioceramics. In that, there are three types. But before I get to those types, I'll just tell you about the journey of bioceramics. In 1892, I think was the first time plaster of Paris was used. It was used as a bioceramic for a patient where he had a hip fracture and they had to specifically use plaster of Paris for that. That was the first time it was used. The next one was the discovery of tricalcium phosphate. They were able to isolate tricalcium phosphate and utilize it for specific bone defects, smaller bone defects, not larger bone defects. And then they were able to do something. They were able to do something better in 1963. They were able to figure out a ceramic bone substitute, which was purely based on ceramics. It wasn't based on TCP or hydroxyapatite. And the use of bioceramics in human surgery came with HAP implants. All these zirconia and all of that came after the 2000s. But till 1980, if you see, bioceramics has been used for a long period of time. Uh, Bioceramics such as HA, bioceramics such as tricalcium phosphate, all of them have a large line of applications. So there's very well documented data. That's why these bioceramics are FDA approved, and they have a lot of applications in specifically when we are exploring in vivo applications in patients. So there are three different types of bioceramics if you look at it. The first one is a bio-inert bioceramic. These generally don't interact with the bone or anything around it. You have bioactive ones. The bioactive ones are the ones that allow that interact with its surroundings, and you have a bioresorbable bioceramic. So these bioresorbable bioceramics generally um, allow for the bones to basically start growing with it. They start to disappear, and the bone ECM, the native bone ECM, it promotes the growth of that ECM. So let me take you through one by one without by giving you a little more examples. So the first one is bio-inert bioceramics. So this you would have seen, plates and screws that are used in a lot of facial reconstruction surgeries, especially in complex surgeries of the hip, complex surgeries of the wrist, of the hand, of the leg. When people get into when people get into very gruesome accidents, they utilize these kind of plates and screws. Now, these do not interact with anything. It doesn't interact with blood. It doesn't interact with any of the body fluids or the bone structure that is already present. They are there specifically to actually hold the structure. And implants, metal, any form of metal implant, the titanium implants, stainless steel implants in the 1990s, alumina, all of these come under this category. They create very good support structures. So example, replacement of the collarbone, or if you're looking at hip replacement, now you get metal hip replacement. So you have a lot of ball and socket joints also that specifically utilize this technology. And there are a lot of companies that are built around bioinert ceramics. Now these ceramics are generally not uh, printed using extrusion based. They are printed in a lot of use cases. Right now, what we are seeing is that there's a lot of printing using powder-based, laser-based applications, where they're using SLM techniques and other technologies to actually powder bed fusion to basically create these structures. And basically, you can play around with the size, with the kind of you can really customize the implant based on the patient. The next one I want to talk about is bioactive ceramics. So these ceramics basically create a direct, they create a chemical bond with the tissue that is there around it. They have a very low, sort of mechanical strength, so they're not used for load-bearing areas. A very good example is glass ceramics. So glass ceramics is anything that can basically interact with the bone and basically holds they use in a lot of implant applications, and they use as fillers. So if you see dental fillers, most of them are those kind of ceramics. They use it after a root canal surgery. The next one is this is the one that is mostly used in 3D extrusion based 3D printing technology. You have bioresorbable bioceramics. So these ceramics, once they put into the body, they are broken down over a period of time. They degrade because the cells in the body start to metabolize these scaffolds, and they start to form these materials, and they start to form their own ECM. When they start to form their own ECM, basically you get a lot of a much more sturdier structure because it's the body's native ECM, and you get lesser rates of rejection as well. Good examples here is tricalcium for beta tricalcium phosphate, hydroxyapatite, PLGA. So there are different materials that are used in this. So these are three types of bioceramics that are basically used, that are basically available. But let me go a little bit into the other applications of bioceramics. So the first is endodontic sealers. So these are basically utilized in endodontic applications for the mouth. Uh, you have root repair, where specifically for root canals and things like that, these are the applications there. Bone grafts, this is one application where people are utilizing bioceramics a lot in terms of bone graft, joint relief, and bone regeneration. Bone regeneration, now people are looking at a different aspect. Clinicians are looking at how you can 3D print a structure and place it, and it's a very a nice way of actually looking at it, because especially when you look at very complicated surgeries, you require a certain amount of customization, because each of us are built differently, right? So that's where you find a lot of applications of bioceramics. So, when you're looking at bioceramics per se, you have, let's talk about 3D bioprinting or 3D printing of ceramics. Here, you're able to control the amount of, porous architecture that is there. You're able to control it from a nanometer to microns. You're able to control how much the pore size should be of the entire bone structure, of the entire scaffold structure. This allows you to basically determine how the cells would move within these scaffolds. How would they start metabolizing the scaffolds? How would they be distributed and migrate? Cells generally do not stay in a stationary position, they tend to move around. And if you're able to create a structure with the right pore size, you're able to induce bone growth. So that is specifically why bioprinting of ceramics is used. You're able to create a very porous structure with very good mechanical strength and biocompatibility. When you're looking at mechanical strength, these things, specifically when you're placing it in the jaw or if you're placing it right below the orbits of the eye, you need a certain amount of mechanical strength. So they use different polymers, blends of different polymers to create that mechanical strength so that it can be placed in those load bearing regions. Another thing, it shouldn't cause any adverse reactions in patients. So I'll tell you a very interesting, an interesting product that came out of one of the IITs. So basically, they created the product for cartilage repair below the knee, and they tried the entire. The biomaterial was tested through and through in rabbits. It was tested through and through in mice, and since it was already an FDA approved material with slight modifications, it was allowed for human pilot study. For the pilot study, they took, I think, around 9 patients, and they did a study where they implanted the material behind the cartilage, behind the knee, basically to reform the cartilage. And what they found out was that they were in out of the 9 patients, only 3 patients were showing improvement, but 6 patients were actually having swelling of the knee. The body was actually reacting. So understanding how compatible your material is or how your material degrades is really important. Understanding whether there is certain bioactivity that can be induced into the material or if it's causing certain bioactivity is also important. That's where bioprinting of ceramics, is a very delicate plane. There are many biomaterials that are approved by the FDA, that are approved by the DCGI for inhuman applications. But when you go to the inhuman applications, when you're changing the molecule even by a little, even if you're changing some of the moieties, I think we'll have to always keep in mind that bioactivity, biocompatibility, and biodegradability are going to be three very crucial factors that determine the success of your bioprinted construct or a 3D printed construct. So why do I keep switching between 3D printing and bioprinting, right? If you see most of these materials, hydroxyapatite, PLGA, PCl hydroxyapatite, and you have tricalcium phosphate. So you have different materials that are utilized in bioprinting. A lot of them have been used in bioprinting and 3D printing, but you can't use the word bio because none of these materials support cell growth. So you can't print with the cells. So generally you're using 3D printing as a technique and not bioprinting. Bioprinting is where you're utilizing it with the cells. But most of these materials do not promote cell growth in their liquid form. So when you're actually printing it in their liquid form, you're printing it and then you're seeding it with cells. So generally we use the terminology 3D printing of bioceramics followed by seeding of the cells. So that is specifically what is done in the process, when you're working with bioceramics, and you use separate binders, and these binders also are not very friendly for cells. So you have different materials that are utilized, and all of these are printed using pneumatic based this one pneumatic based approach. And you have different variations of these biomaterials that are approved by the FDA and that are being used across industries. So I'll just quickly talk to you about a little bit of the bioactive side. So when we spoke about bioactive side, the bioactive bioceramics, there are certain active ingredients that are added to the bioceramic to actually increase, the functionality of the selected insert. So this is a 3D printed structure. So here you have pure TCP, you have 2.5, this one 2.5, 5, and then you have 10. So this is basically what they've done is they've increased the concentration of zinc in each of these scaffolds, and basically they're trying to see how does an increased quantity of zinc improve the cell adhesion and the cell behavior within the scaffold. I will share this paper with the organizers so that you can get a little bit more understanding about what basically can be utilized and what they've done, what can be utilized when you want to activate your biopolymers. The next one I'd like to talk about is a hollow structure. So here, um, generally our bones also have arteries and veins going through it. So this study basically compared the a manner or a technique to actually print, print a bone with the hollow structure in between, so that veins and arteries can be promoted to grow. So imagine you have a structure where you have veins and arteries that are growing within the hollow structure. That is specifically what this structure shows. You have this entire hollow structure with that they've printed. They printed in the form of a scaffold. This is an SEM image, and basically they what they understood was that when they printed with TCP, the compressive strength was good. It was comparable. When you're looking at BRT, the compressive strength was a little bit on the higher side, but when you print with BRTH, it was similar to what you would find in the bone. So they wanted to see how they could get the bioactive portion also much better. So this was specifically, what they utilized this, this hollow structure approach for. So with that, I'll just go to maxillofacial reconstruction. This is a very good application of 3D printing for bone-based applications. So we ourselves, when we started out as a company, we reached out to doctors and we wanted to really understand how can we understood how to operate 3D printers. So we wanted to see how can we help patients. And when we worked with doctors, we understood that you can actually create 3D models such that the surgery times for doctors actually comes down. And that's where we were able to work with multiple doctors and create multiple 3D structures of patients' jaws using their CT scans, CBCT scans, so that they can get a good understanding of what exactly is the defect and what exactly they have to do within the surgery. So here is another, very good aspect of where they created an entire year construct just utilizing, 3D printing technology. So in this case, I'd like to talk about a study that was done in, I think this was in New York. I'm forgetting the university's name, I'm sorry, but basically what they did was the girl was born without the ear, and they basically created a ear from her left ear was not fully formed from birth, so they took the right ear, created a mirror image, and they were able to print it using PCL. So it basically looked like this, and once they printed it, they were able to implant it and they put the skin on top. So when they close the skin, they wanted to now they are doing an extensive study to see whether the vasculature is actually formed and if the cartilage is actually formed properly. So that is something that they're doing. So the material that they used was PCL, and they were able to create the structure. So this is a very interesting year reconstruction study that they did at a university in New York. So, with that, let me just quickly touch upon what are the barriers to clinical translation. So one, it's when you're looking at the post-processing steps that are required, or when you're looking at how time-consuming something like this can be. Um, Printing bioceramics is never easy. They're very difficult to deal with because you're dealing with the brittleness of these structures. You're dealing with very nuanced temperature control situations that you need. And prefabricated bioceramic scaffolds often fail to match the anatomical shape. So that's where you need technologies such as bioprinting that come to the fore. You need to create biomaterials that can improve the state at which these materials or these cells, the chondrocytes, can actually form a tissue. So that's basically why people are looking towards a bioprinting approach rather than a 3D printing approach like what I showed you here. Here they would basically create the structure and then seed the cells, but then you have another way of approaching this where you can actually print the materials with the cells. So this is the approach that bioprinting offers. So people are exploring that as well. So there are a couple of ways to actually explore this technique. So I will touch upon that in some of my future slides on the work that we did with some of the universities. So this is one video that I wanted to show. So this I'm going a little off track so that I can really show you what bioprinting can do. Basically, they utilize this technology called Fresh, FRESH. It's a form of embedded printing. So you're printing within a gel. And here in this video,
This is the first time that the whole cellular heart with blood vessel is.
so they printed this. So they printed this entire structure just utilizing, I'll just keep this aside. Yeah. So they printed this entire structure in a gel bath. So I'll show you basically how they printed it. Yeah.
Stem cells and then differentiated to become.
They formed it layer upon layer. This is the size of a rabbit's heart. Okay. They were able to print the tissues. They were able to print the arteries. They were able to print, the structure as such of the heart. But they weren't able to get the microcapillaries. They weren't able to get the nerves. Now they're trying to go one step ahead and see how they can get the microcapillaries and all.
Cardiac cells and cells that form blood vessels, and the biomaterial, the collagen and other sugars that in the tissue is processed to become a bioink, and together when mixed.
So this is one of the earliest applications at Tel Aviv University that they worked on. The next one I wanted to show is bioprinted lungs. So here, basically, they were able to create a three-dimensional structure using the same fresh technology, the embedded printing technology. But here they were able to create an alveoli and they were able to create a sac around it. So here, if you see, so you can see the central line. Actually, this is a central line with the wind. I mean, with the oxygen going in and coming out, and you see the sort of alveolar structure forming over here. The capillary structure forming over here. It's a very beautiful video. So you see that they were able to form the entire capillary structure, and within that, they were able to form the alveoli. Imagine the applications that you could work with. You could actually create a small miniature working alveoli within a lab that can be used for testing. This is one of the I think this was a few years ago, and this was by Rice University, and a very good publication, and it's one of the biggest breakthroughs that bioprinting has seen in the recent years. So this is a really nice way of looking at how we are slowly but steadily working towards a more clinical application. Um, this is one of the ECM components that was actually printed at IIT Hyderabad by Dr. Falguni Pati and team, and they were basically able to entirely suture the cornea onto the flap. So basically, if you see here, they're actually suturing the entire cornea, and they were able to get a very, very good sturdy structure. So this is one thing, in which bioprinting has a very good application, when you're looking at printing of cornea. So with this, I'll just quickly touch upon, we're doing a lot of work across the country with a lot of institutes. We are working with each of them at different capacities. For example, King George Medical University is looking at 3D printing of bone for oral maxillofacial reconstructions. We have Manipal University that's working on cartilage. And then another university which is working on bone was Somaya Vidya Vihar. They just published their work, where they created an alginate and a bioceramic mix. This was a very good application that they looked at. So we have a lot of applications that people are focusing on with respect to bioprinting, but I want to touch a little bit upon what the work we have done with the different universities. So this was one of the first work where we printed a material called PCl, polycaprolactone, with trifluoroethanol. So this was printed onto slide discs in different combinations. So basically, they wanted to see how breast cancer cells behave in a three-dimensional environment and how these cells basically behave with normal cells, breast cancer cells versus normal cells in a three-dimensional environment, given different layers and different ways of actually, different designs that we can actually create using 3D printing. The next one I want to talk about is IIT Roorkee. So this was a very nice corticular bone structure that we had printed at IIT Roorkee using pneumatic-based bioprinting. As you can see, you have larger grooves and then you have the minor grooves over here. So this was basically to see how this entire bone structure can be formed. The corticular bone structure can be formed with a central, with a central holding line and with branched structures on each side. So this was actually printed using pluronic F127, but we wanted to see if we could actually get this structure. And this was one of the key applications that they wanted to focus on. The next one was a project that we did for a researcher at MS Ramaya here in Bangalore, where he wanted to test with small animal testing. So we were able to create these really nice structures using a slurry of hydroxyapatite and beta tricalcium phosphate, and we were able to create these very unique structures that we utilized for animal experiments. The research sadly didn't get recognized for further funding, but the good thing was that he was able to generate a lot of data, that could be developed using this scaffold. Then we have this, which was at D Patil, Kolhapur. Here they've developed a decellularized ECM-based biomaterial, and here they're printing the topmost portion of the finger. And basic application is to see if you can create a three-dimensional structure utilizing just a biomaterial. And this biomaterial was actually a UV cross-linked. So it allows you to create a very nice, beautiful structure over there. And obviously, finally, this was the work that was done at Shastra University in Tanjavur, where they are developing different types of biomaterials that can be utilized for bone regeneration studies. So with this, we've worked across the board. We've worked across the entire seam of bioprinting, where we have explored different aspects, right from basic cartilage development to bone-based applications. But now what we're doing is we are spreading our wings wider. We are exploring different aspects of bioprinting, such as organ on a chip. We are looking at space-based bioprinting, which is really, really interesting for us. We're looking at hollow organ printing, so we're looking at tubules. We're printing. If you see our social media, you'll see a lot of work related to embedded printing, or we are also working on coaxial and triaxial printing, which allows you to print one biomaterial within another. We are also specifically focused on defense-based applications. So that is one of the key things that also we believe that we want to provide for the future of the country as well. And yes, more importantly, what we do is we collaborate. We work with a lot of people in the space of bioprinting and in outside the space of bioprinting, and we look at how we can collaborate and really take this technology to its true applications, which is more clinically oriented. With that, I will end my talk here, and I'll open it up for questions. In case you all might have any questions, I'll be happy to answer them.
Thank you very much for our wonderful presentation, sir.
Thank you, Dr. Venkatesh.
And I request participants, if you have any doubts, you can take the advantage of the chat box, or else you can raise your hand. With that, I can enable your mic.
Yeah. I think someone has raised their hand.
Raghavendra sir, you can unmute yourself and you can raise your query.
Sir, good evening, sir. My name is Raghavendra. Actually, you said that blending of ceramics with the polymers for enhancing the mechanical properties. You said, no, sir. What type of polymers we can blend with this ceramics like HF, TCP?
So basically, it depends upon the kind of application that you're looking for. If you're looking at cartilage or bone, it depends upon what tissue type that you're aiming for. So that is the first thing that you have to answer. Second thing is you can mix alginate. Alginate generally it works well with a lot of different bioceramics. Specifically, using bioceramics, alginate is mostly used in these kind of applications. Uh, Once that and able to actually vary temperatures, vary kind of printability of these constructs. And finally, what we did was for the MSR project, we utilized polyvinyl alcohol. So this polyvinyl alcohol created a perfect binding agent that allowed for the printing of the slurry. It allowed for the printing of the slurry in very complicated structures.
Sir, which printing technology you have used, sir?
We use extrusion-based, pneumatic extrusion-based bioprinting.
Sir, can we customize that materials in pneumatic such machines? Because many
100
machines will come with built materials, no, sir, like
I-
specific
No,
materials.
yeah, that I feel is a I think everybody in the bioprinting space believes that, but what we truly believe is that the bioprinter has to work for you, right? If they tell you, okay, these are the set of biomaterials that you can work with only, then that doesn't work. You have to create your own biomaterial and work with it, and that's when actually you see true progress in the field. And you with pneumatic based bioprinting, you can 100% go and explore different applications of the technology with different biomaterials. You don't have to hold yourself to one biomaterial. Our machines are at least built that way.
Sir, can we utilize? How can we utilize that such material machine, sir? Like I'm a student, PhD students actually. How could
Okay.
we utilize like a payment basis? That what location we can utilize such for
So
experimentation?
yeah, you can utilize it for experimentation. So where are you based out of, Dr. Raghavendra?
Sir, I'm from Nizamabad, sir. Actually, I can come to Hyderabad as well.
Yeah, so we have a machine at Hyderabad at NIAB, Gachibowli. And we have one at IIT, but IIT machine is really small. It's inside the cell culture room, so I don't know if you'll be allowed there. But specifically, if you want at Gachibowli, there's National Institute for Animal Biotechnology, and our machine is there as well. You can utilize it there. I can
Sir.
talk to the team there, and I can connect you.
Okay, sir. Can you share your contact details, sir?
You can take it from Dr. Venkatesh. He has my details. If
Okay,
that's
sir. Okay. Thank you very much, sir. Thank you.
thank you.
It would be helpful for me a lot.
Yeah, no
Okay,
worries.
thank you.
Happy well.
Thank you, sir.
And any other questions from other participants?
Probably they can leave the questions in the chat box as well, Dr. Venkatesh.
Yes, sir. Dear participants, if you have any questions, you can leave it in the chat box.
Yeah.
We have
Yeah, I think yes. So we can use polysaccharides with polymers for sure for bioprinting applications. There are a lot of documented data in terms of how polysaccharides can be utilized, and especially polysaccharides help in the cell health. You know, when you're keeping the cells in a bio ink, it really helps. Polysaccharides do help in a very big way. So yes, you can use a blend of that with the polymer to actually create different the kinds of biomaterials that can be utilized. So my mic is unmuted, right?
no, no, not yours, sir. I'm telling you to the.
Sir, can we use polylactic acid blends with ceramics for biomedical?
Polysaccharide blends with ceramics. That's what you said?
Sir, polylactic acid, PLA.
PLA with ceramics. Yes, yes, 100%. There are a lot of things with that. You get it readily
Okay, okay.
available in the market as well.
Uh-huh.
Yeah.
Okay, okay.
So you can do that. Not a problem.
Okay, okay, sir. Thank you, thank you.
Yeah.
Yashwant Kumar, sir, you can unmute your mic, and if you have any doubts, you can raise, sir.
I think he's having a problem with his mic.
Yes, but I give rights to him to speak also.
Okay, his doubt is cleared. That's great.
Okay, then
Yeah.
good, sir.
Anyone has any other doubts, you can please leave it in the chat box and I'll be more than happy to answer.
And personally, I have few doubts, sir.
Yeah, sure.
Uh, are you developing laser-based bioprinting technology at your facilities, sir?
No, currently we are not developing laser-based, but we are, however, looking at light-based printing. So that's one of the applications that we're looking at. So we're looking at DLP technology and SLA technology. So these are technologies that we're exploring right now that have applications in bioprinting.
And do you have any technology connected to bioprinting, sir?
Sorry?
Sorry, not silicone printing.
Sorry, I can't.
Do you have any technology connected to silicone printing?
Silicone printing, not at the moment. We don't do silicone printing at the moment because one, it requires high temperature and we generally are in the biospace, right? So we generally work with those polymers that go only up to 250 degrees centigrade. That is a space that we touch. We push that boundaries. If it comes to that boundaries, we can do it.
Okay, sir.
Sir, I have one more question, sir. I have one question.
No, 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 please.
I'm from mechanical engineering background, sir. What kind of research work we can take up, sir, like in biomedical applications and at the same time with 3D printing?
I think, see, uh, one application is when you're looking at 3D printing, right? You are exploring different, see, right now, whatever is there to be explored with the technology has been explored, right? Because 3D printing is a 30-year-old technology. So that is one. The second one is when we are looking at the game-changing aspect here is to study, biomaterials or bioceramics once they are printed. A good study would be, to understand the stretchability of the biomaterial, the porosity of the biomaterial, the compressive strength of the biomaterial, because specifically these are that are used in load-bearing sessions, right? Load-bearing regions of the body. They need to have good compressive strength, ensuring that when you put this polymer, how does it interact with the bone? These are studies that are actually required. As a mechanical student, I think whatever is there to do with the mechanical aspects of a bioceramic scaffold, you should explore that aspect. That is one thing that I would say would actually give you a very good edge over a lot of other people, because not many people have worked on bone-based printing applications and studying that applications. Not many people have worked on that. Although there are many people who have worked on bone, a lot of people who are working on bone. Currently, AIMS is doing a phase 2A or 2B clinical trial where they've actually printed the bone structure and they are implanting it for minor fracture corrections. This is a study that came out of IIT Bombay that got translated, and that person is a mechanical engineer. So I think, although you're a mechanical engineer, I would say go beyond your comfort zone and see what you can do in the space of 3D printing and bioprinting, specifically with respect to materials. I would say that is the next biggest thing when you're looking at this space.
Like means synthesis of new materials and experimentation and new blends is what you're
Yes,
saying, sir.
yes. Synthesis and testing both.
Then characterize materials
Yeah,
for mechanical
yeah,
properties.
yeah. I would say you should look at that.
Thing is, now you given options are like Gachibowli, but whenever I'm exploring the for experimental setup or machines, whatever the machines I got is like they have inbuilt materials. And even NCAM also they said whatever the materials they have, they can use those materials only. We cannot customize the materials for experiment. That is the thing I got. Anyhow, you said
I mean, you can look at setups. See, that's with what your university has at the moment, right? So what I would say is, even we also had that, we had that barrier. So what we did was we reached out to IISc. We understood IISc has an equipment that is specifically allows for third party materials and also to be tested. So we were able to test the stress and strain studies. We were able to test rheological characteristics. We were able to test the compressive strength of the biomaterial. This is not only for skin, we were able to test for bone as well. So across the board, we were able to test. So I would say go beyond the universities and see what you can do. And obviously, you have since you can go to Hyderabad. I think you can approach NIB, which where the one of our very good friends of the company, Dr. Janani Radhakrishnan, is doing some good works in material science. She can help you and guide you in that sense as well.
okay, okay.
Yeah.
Thank you.
I think Dr. Richa said. Uh, which porous scaffold is used in tissue engineering? So, in case of hard tissue engineering, Dr. Richa, there's a lot of applications. I spoke about it right now. In soft tissue engineering, there are many biomaterials that are used, such as gelatin, collagen, alginate. You have gelma, methacrylated gelatin, methacrylated silk. You have PVA, you have cellulose, chitosan. There are a plethora of biomaterials that can be utilized for printing soft tissues. So just the same as bioceramics, there are so many different combinations that you can try these materials in. I just named a few, but there are so many that you can utilize to create porous scaffold structures. Again, the porosity also determined by the weight by volume of your material and everything. So it depends upon that. But yeah, I think that determines what kind of porous structure that you would get. And yeah, so I would say that determining the weight by volume of the mix of your biomaterials is a key component of what this entire printing of soft tissues is all about.
Sir, I have another doubt. As per your knowledge, whatever the bone scaffolds are different components of, I mean, different things of the human body we are trying to produce.
Yeah.
When it comes to the actual practice,
It comes to the actual.
practice, I mean,
I think
when it's possible to place in.
bone, see, right now they're looking at avascular structures, Dr. Venkatesh. So immediately they're not looking at something that is highly vascularized. They're looking at cornea, they're looking at skin, they're looking at cartilage of the ear. So these will be the initial ones. Then you will get to the valves. So valves will be about 5 years down the line, I would say. Bone can be as soon as another 3 years down the line. And then you will see applications such as liver and all of that, more complex organs coming to the fore, probably 10 to 15 years down the line, because you need the regulators and a lot of other people and the government to also play a very important role here. So it's not just one, it's multiple people who are coming in to actually make this happen. So I would say fully functional organs might take 50 to 20 years down the line. You can have avascular organs, avascular structures such as bone, cartilage, just the top portion of the skin. All of these can be grafted, printed and grafted. That and cornea. So these are all things that are quite interesting and can be done quickly.
Okay, sir, thank you. Any other questions from the participants?
So I don't think there are any other questions, Dr. Venkatesh.
Yes, yes, sir. And thank you very much for your wonderful presentation, sir.
Thank you so much, sir, for having me.
Sir.
Thanks to all the participants as well. Thank you.
Thank you, sir. Thank you very much.
And dear participants, you can take a few minutes of break, and we will start the next session exactly at 7:30 p.m. Please don't leave the meeting. Please stay back in the meeting and take break for a few minutes. Dear participants, we are waiting for the speaker presence. Once he is there, we will start the session. Hello, Kranthi sir. Good evening. Am I audible to you? Hello, Kranthi sir. Please unmute your mic, sir. Kranthi sir.
No, sir, your voice is not audible to us. Now it is audible to us, sir.
Is it clear, sir?
Yes, sir.
Okay.
Can you share your presentation, sir?
Yes. Is it visible, sir?
No, sir.
So I'm sharing the window, right?
Okay, you can share either window or your presentation.
It's taking time.
Okay.
Is it visible, sir?
No, sir.
Just a second. Is it visible?
Yes, sir. Okay. Yes, sir. It's visible and select screen share. Yes.
Shall I start, sir?
Just a minute, sir.
Hello. Shall I start, sir?
Just a minute, sir.
Okay.
Initially, I would like to introduce yourselves to the participants. Good evening, participants. Our today's session will be handled by Kranthi Kumaruji. Dr. Kranthi Kumaruji is accomplished academic and innovator with 14 years of teaching experience as well as research experience. A pro native of Varangal, he holds PhD degree from NIT Raipur and has made significant contribution in academics and industry. As the founder of Susan 3D Tech, Dr. Krantikumar G specializes in advanced additive manufacturing technologies. His research portfolio includes cutting-edge projects in artificial intelligence, machine learning applications in the health sector as well as transport vehicle sector. With this brief introduction, I would like to hand over this session to the Kranti Kumaru sir. Sir, please continue the presentation.
Good evening, sir. Myself, Dr. Kranthi Kumar Guduru, founder and CEO of Susan 3D Tech, which is a additive manufacturing materials and manufacturing company. So started in 2023 in Warangal. So handling some MHRD projects from NAT and IITs concerned. So I'm here to express my views on the functional graded additive manufacturing and the scope of AI in manufacturing sector. We shall start with the contents in this scenario, that is additive manufacturing, methods in additive manufacturing, applications, functionally graded materials, types and applications, functionally graded additive manufacturing, processing of functionally graded additive manufacturing, applications, challenges, as well as the AI, scope of AI in manufacturing sector. Concludes with the references which have been taken. What is the additive manufacturing? Additive manufacturing is a layer by layer manufacturing technique by using the 3D CAD data, by using the physical prototypes, so which is a quick method compared to the conventional.
Sorry, sir. Sorry to disturb you, sir. And
Yes.
we can able to see the first slide of your presentation. We are unable to see the next slides, sir.
Contents.
Yes, sir.
Are you able to see now?
No, sir.
Finish sharing now.
Okay, you please do one thing, sir. You stop sharing. I mean, you stop presenting your presentation from slide share mode. Just stop
Okay.
it.
Okay.
Now you please share your screen again, sir.
Okay. Okay.
Yes, sir. Your slides are visible, and please don't select slide share mode, sir.
Okay.
You please disable slide share mode, sir.
Uh,
Yes, sir. Like this, you can initiate. Again, we lost your screen, sir.
you get it now?
No, okay, sir. And please continue your presentation, sir.
Okay. So we'll start from the contents, continue from the content section. Is it visible, sir? Hello?
Yes, sir. Visible, sir.
Okay. So we'll continue from the contents. So in this juncture, continuing with the contents. So in my part of explanation, start with the additive manufacturing. So contents are additive manufacturing, methods in additive manufacturing, applications, functionally graded materials, types of applications, functionally graded additive manufacturing, process of functionally graded additive manufacturing, applications, challenges, and then followed by the scope of artificial intelligence as well as machine learning in AM process. So we all know the rapid prototyping. So later on, it has been named as additive manufacturing or 3D printing. Simply, this 3D printing is nothing but a layer by layer manufacturing technique by the use of a 3D CAD data to manufacture the prototypes as well as the functional models. So here, this is a process where the CAD model has been designed, and that design is fed to the 3D printing machine or 3D printing device, which will be produce the 3D model or 3D model prototype. This is the process of 3D printing. So CAD model, design of CAD model, which is sliced, which is transformed into the .stl file or .obj file, which is to be sliced into the number of layers to be printed in the AM system. And the last part will be the finished by using the post-processing section. Later on, we'll get the fully manufactured the object from the 3D printed device or a system. These are the several modes in additive manufacturing has been introduced earliest. So those are material jetting, vat polymerization, binder jetting, material extrusion, direct energy deposition, sheet lamination, powder bed fusion. So in our Suzanne 3D Tech, so we have three types of machines, that is material jetting, vat photo polymerization, binder jetting, as well as the sheet lamination. Advantages of additive manufacturing. So apart from the compare with the conventional manufacturing processes like molding and casting processes, we don't need the molding and casting processor. We don't need the molds or casts. Simply, we'll get the object by using the 3D design. According to the design, we'll get the 3D printed material or a design, whichever we have decided in complex shapes or complex geometry, as well as we can print or produce the objects from smallest objects to the largest objects, as well as we can print the multiple objects of a part we have designed. The number of parts of one product can be designed at once in the 3D printing. Then go for the applications of additive manufacturing. We have several applications in our domestic as well as the industrial purposes. That is in invention and validation, form, fit, and function of different materials, wind tunnel applications, patterns for casting, jewelry design, direct tooling, reverse engineering, medical prototyping, as well as naval and aeronautical parts. So materials options for 3D printing. So we have several material options produced in these 3D printing models, where the metals as well as the non-metals, polymers, powders, biocompatible materials such as PCl, PPE, as well as TCP, PLA, and much more materials, as well as the composite materials also we can use in a nowadays. Limitations, we have some of the limitations, despite of many advantages we have, that is cost, accuracy, finish, strength, material options. Why? Because compared to the conventional processes, the initial investment for the AM machines are costly, quite bit of costly, rather than compared with the conventional molding and casting machines. Accuracy also. So finish. So some of the materials have not with the mere finish compared to the conventional molding processes, as well as strength too. So we have the material options. So there will be materials limitations are also arising in this additive manufacturing, but these are we can overcome these limitations by using various processes in additive manufacturing, like composite material, functional graded material, as well as the optimal printing process techniques can reduce these limitations in additive manufacturing. However, so as I said, we are discussing now the concept of functionally graded materials in additive manufacturing. Actually, what is functionally graded materials? When come to the composite material, so the need of composite material is to enhance the material property as well as the uh, material comfortability when we use in a product manufacturing. So if we see the picture A and B, simple composite material, mixing of composite A and B, where the property has been abruptly changes at the interface of the mixing of those two materials. On the other hand, in the FGM or functionally graded materials, it is gradually varies from point A to point B, or from material to the material A to the material B. So this is the beauty of the functionally graded materials. As we see in examples, if we print, if we suppose we take stereolithography or fused deposition modeling, a polymer lattice structure has been printed with the circles represented with the A as well as the triangular portions. So these two lattice structures, see the grading from the top surface to the bottom surface. So we have the gradient level from the top to the bottom will decide the nature as well as the metal property of the uh, design as well as the outcome of the product. So these are the types of gradation. One is coating of FGM material, another side is bulk FGM. So we have this thermal spraying, laser cladding, electro photoactive deposition. So on the other hand, foaming of polymers, gel casting, wet powder spraying, directed solidification, jet solidification, powder metallurgy, sedimentation. On the other hand, coating FGMs, that is PVD, CVD, chemical solution deposition, surface reaction processes like nitriding, carburizing, and so on. Applications. So there are plenty applications in functionally graded materials in streams of nuclear energy field applications, medical and biocompatible applications, defense, military and armor applications, aerospace applications, energy sector applications. Next, optoelectric and semiconductor conductor field. So now we are using and going for the EVs. So where we are going to use these FGMs, especially in semiconductors. Semiconductors used to be in EVs, and the other applications, cutting tool applications, turbine blade, heat exchangers, and etc. So in the glimpses of functionally graded materials, simply defined orally, that is functionally graded material by using additive manufacturing, which is a layer by layer technique that involves the gradationally varying the material organization within a component to meet an intent function. Maybe it is a strength, maybe it is a structural geometry, maybe it is a color and other aspects. The second one, the advancement of AM technologies make it possible to strategically control the density and directionality of material deposition within a complex 3D distribution, or to combine various materials to produce a seamless monolithic structure by changing deposition density and orientation. For example, in fused depositing modeling, we are giving the material to be printed with the 100% density or 80% density or 50% density. So likewise, we are going to print one object with a constant density or and constant dimensions. Once we designed one 3D model, so that dimension won't be changed until unless it will be interrupted in between when it is going to print or disturb the printing. So now in Ultimaker 4.4.1, we have the one option for the gradual density modification, as well as the size modification also given in the special category. So you can also see in that Ultimaker software also, slicer software. So where we can do the FGMs, that is functionally gradation, while printing from bottom layer to the top layer of a polymer. And the third one, the potential microstructural gradient compositions achievable by FGAM can be characterized into three types. One is variable densification within a homogeneous composition. Second one, heterogeneous composition through simultaneously combining two or more materials through a one gradual transition. And the last one, using combination of above two, that is variable densification with the heterogeneous composition, that is combination of more than one material. So that we can see in example. So this is the one example for the gradually decreasing the density in a concentric geometry. That is in first figure is the a concrete structure, and the second one is the natural palm tree, where the circular gradation has been observed in there. So we can see here the conventional multi-material additive manufacturing versus multi-material functional graded additive manufacturing. So in conventional multi-material additive manufacturing, so we are combining any two materials. For example, we are going to manufacturing one block square, so with the dimension of 20 mm. Up to 10 mm, we are going to print the with the PLA material. Above the 10 mm to 20 mm, we are going to print with the ABS material. So this is not the FGM actually. That is a combination. So we don't call it as a FGM. We called an FGM, that is a functionally graded material, where the gradation is meant to be slowly with the dimension as well as the material from point A to the point B. So that we can see in second one, that is multi-material functionally graded additive manufacturing material, where the gradation has been visible, that is A plus B. A is the one material, B is the another material, A plus B. The gradual combination, whether it is a structure in it, density in it, or a material combination, whatever it may be, heterogeneous or homogeneous, or combination of both two. We'll see one schematic mode of functionally graded additive manufacturing. Firstly, the one-dimensional gradient. Second one, two-dimensional gradient, as well as three-dimensional gradient. We can imagine one-dimensional gradient in the sense in one direction, or length or a height. In two-dimensional, length as well as the thickness. Three-dimensional gradient, as we have seen in this previous video, previous slide, just like in palm tree. So this is the types of gradation classification, that is design and modeling. This flowchart has been explained here. Design and modeling of a 3D model or an object. For that product, that is the material as well as the manufacturing. Whether you take the fused material extrusion or material deposition or binder jetting, or you say you can direct energy deposition like laser in metal 3D printing. So third step is additive manufacturing, and fourth one is the post-processing of that FGAM, and the last part will be the finished product from the FGAM. And we can see more examples for these homogeneous, heterogeneous, and homogeneous plus heterogeneous FGAMs by using 3D printing. If you see the part A, there is a, in this lattice structure, so you all know, familiar with the lattice structure. So that is lattice structure has been designed with one particular lattice, whichever the dimension we can decide. So that lattice structure, the combination of that single cell, so that is sustained in whole structure, which is called as a lattice structure. In this, the lattice, the cell size is fixed. In figure A, for example, this is one type of FGAM, one type of gradation, that is in this lattice structure, the cell size is 6 mm with the density varied from top layer to the bottom layer or bottom layer to the top layer. So if you can say in stereolithography, top layer to the bottom layer. So then the manufacturing mode is in that type, you can say. In fused depositing modeling, we can start with the bottom to the top. So whatever it may be, the gradation, the density gradation from top to the bottom or bottom to the top, the variation in density is simple, the homogeneous gradation. The second one, the cell's dimension is 6 mm, as well as the dimension is the density, the infill density of that structure is 30%. But for few layers, if we say this lattice structure has 20 layers, from bottom to top 10 layers would be one material. Above 10th layer, the 11th layer to the 20th layer to be to be fed by the another material. Just like I said early in fused deposit modeling, just like PLA, combination of PLA as well as ABS. So this is the heterogeneous mode. Third one is the cell size is varying from top to bottom linearly or bottom to top from 2 mm to the 6 mm with the constant infill density 30%. See here in C, the cell gradation, this is called as the dimensional gradation or geometrical gradation. So we call it as a geometrical gradation, not the material gradation, it's a geometrical gradation. So in this, the top layer cell is 2 mm. Gradually, it will increase from 2 to the 6 mm. So these three types of modes, we can use the functionally graded gradation in different types of materials as well as compositions, both in geometry as well as composition. We can combine the geometrical gradation as well as the material composition also. So that is the beauty of functionally graded material by using additive manufacturing. So methods as well as materials for FGM, you can see. So this is a summarized thing for materials as well as the manufacturing processes in additive manufacturing. That is a fused depositing modeling. So we can use the thermoplastics, ceramic slurries, metal pastes. So when we go for the selective laser sintering, polyamides, polymer, atomized metal powder. When we go for the direct metal laser sintering, as well as the direct metal deposition, ceramic powder, metal sheets, as well as the metallic filament. When we use the laser, so we can use the metal filament also, and the polyjet technology, photopolymer, digital materials, which are used in making the shoes as well as the toys. In detail, we can see multimaterial stereolithography processes based on bottom-up projection. So this is the simple. In first figure, we can see the multimaterial stereolithography process based on the bottom-up projection manufacturing method, where the resin can be replaced. So we can use more than one resin according to the geometry we have given. According to the CAD model, we have produced by the design and fed to the stereolithography system. For example, we are seeing that Adidas is making this multi-material stereolithography, TPU material, rubber material. So making of shoes as well as the sports utilities. Second one is the triple extruder mechanism design. So in this FGM, so we can see the material A, material B, material C. The percentage of these three materials has been defined early as per the definition as per the percentage of material fed to the machine or defined by the machine. So we can print accordingly with the gradation of percentage of different materials as well as the different materials also. One is TPU, polymer. Another one is the hardest plastic, just like ABS, PLA, nylon. We can combine these these materials with the rubber materials, just like TPU. The third one is we are using the lens technique. So this lens technique we have seen this machine is available in Wipro, that is around 10 crore. We can use this material lens setup. The different powders can be supplied. So different powder material can be supplied, just like as we have seen in picture B, the percentage of material, combination of material, composition of material to be deposited directly on the base. And second one is the SLM. You all know the SLM machine, the powder bed fusion. So in powder bed fusion, I already have experienced with the powder bed fusion. So we are unable to make the gradation. Why? Because the gradation is not that much effectively coming from the bottom to the top when we go for the multi-material there. So that is the best method for the metal FGM is only the direct energy deposition. That is just like DMD or laser technique. Another one is this is the example for the polymer FGM. So in this, nylon as well as the nano silica particles are combined to design and develop a FGM polymer material. It is a gripper actually with the layer size of 7.62 mm. Another beauty of this functionally graded material is the 4D printing, as we have seen in many research papers as well as the videos now. They are exploring, many researchers are exploring the 4D printing, which is the functionally graded materials. So functional materials. So functional materials by using 3D printing. So far we have seen the 3D printing or rapid prototyping of polymers, metals. Now we are using the functional materials. Those are the functional materials, just like simulators. So when applied a temperature, when that object is going to expose with the temperature or a load or a light or a shock, so that will respond within a time, as well as for the time duration also. After some time, it will be remodel itself as per the designed criteria, designed dimension. So in this, one more example, one dress has been designed with the customized dress with the our 3D model with the patterns of triangles. So which is simulated and printed with the 3D printing material with the SLA, that is stereolithography, as well as the SLM or the poly jet also. So we can able to see. So in future, the specially designed shoes. So whatever this shoe already we have seen the functionally graded material by using polyjet materials. So polyjet printing, that is the multi-jet printing by using SLA or SLS. And one more example, the self-repairing active pipes. So we don't need the mechanical pumps. Okay, so recently we have many accidents encountered in the aeroplanes with the malfunction of the mechanical pumps in retrieving the flaps of a aeroplane, which are used as a brakes, as well as these mechanical pumps which retract the landing gear of an aircraft. So the general problems occurred by using the pumps as well as the pipes, the hydraulic pipes, or the pumps were worked to retract or able to land the aeroplane smoothly. So these are the problems where the those problems can be rectified by using these self-repairing active pipes. Sometimes those pipes will be leaked in joints. So sometimes by using the by the extreme pressure from the surge tank of a oil pumps where the oil will pass through these pipes will create a unwanted disruption as well as the damage of pipes in the you can say what do you call joints especially. So the leakages, the mainly the leakages of those oil leakages may cause the fire accidents in aeroplanes, will cause the malfunction of these aeroplane landing gears as well as the flaps which are used in brakes of aeroplanes. So that can be replaced by using these self-repairing active pipes, so which are made from the polymers as well as the functionally graded metals also. See, one is the self-assembling products from two-dimensional to the three-dimensional. So furniture, we can see adaptive furniture. And one more example, adaptive supporting and assistive textile apparel as well as footwear. So in future, we are going to see this 4D printing, the functionally graded material, which is printed by using 3D printing. So which are being used in, for suppose we can say, which exposed to the light, which exposed to the pressure, which exposed to the color, which exposed to the heat, which exposed to the cold. So whatever the climate conditions and the say the ease of doing for the human being welfare. So we are going to use these 4D materials, 4D printing for the easiest way of life. We can see in future also. So one more case is taken from one more research paper, that is the combination of metals. So we can see here the schematic diagram of the functional graded material printed from the laser, that is direct energy deposition. See here in first figure, the multi-material FGM part of copper, chrome, zirconia, and tool steel using laser-based powder bed fusion embedded cone shape into the copper, chromium, zircon cone. So this is our the desired part where that researcher has manufactured the desired part. That cone part should have this gradation of copper, chrome, zirconia with the proper gradation. The second one also, one more example, one more case study has been taken. The schematic and photograph of gradient alloy specimen. The dotted line shows where the part was sectioned for analysis. You can see three materials, three different materials. So this is the utmost challenge. This is nothing but the heterogeneous manufacturing by using laser. Why? Because in direct energy deposition or laser machine, there is a problem with the material deposition with energy. So we can deposit a material which at once we can print that material. So we cannot combine with the another material. Why? Because the melting point is a main criteria. See, so inconal is the inconal 620. Inconal you can see inconal 600 grade, 700 grade, inconal steel, as well as the stainless steel, marine steel. So these are the having the these metals having different and distinct melting points exhibiting over there while we depositing on the bed. So that is the main challenging. So that challenge has been now slowly that is overcome by using the laser machine as well as with the optimal printing process parameters. While say the printing parameters just like we can say the temperature, the layer height, the time, and the density of material. So these are some of the primary and imperative printing parameters which have been optimized in such a way that that gradation can be achieved. So one more example in case 3 also, that laser metal deposition LMD was employed to explore a new fabrication process for producing a functionally graded material FGM from titanium 6A aluminum 4V. So this is the aircraft graded material which has been printed from LMD. See, the gradation from phases from Ti6 aluminum and 4 vanadium to SS316. So gradation, we can see that gradation SS316 ferrous element, chromium element, as well as the vanadium element towards the Ti6 aluminum 4 vanadium element. So this is the simple structure that is a that is printed with these printing parameters. Output wattage 1000, 1700, 550. Beam diameter, can speed, shielding, gas, organ, powder bed, powder feed rate, that is 5.1, 6.3, 7.6, 7.2. According to that machine feasibility, that parameters have been taken to print these Ti6 AI AL 4V vanadium 4V gradation material printed in LMD. So there is a difficulty. Still, the researchers are getting with the combination with the multi-material. So other than the multi-material, for suppose we can say the dimensional gradation is possible very easily in the this laser metal deposition or direct energy deposition. So when we go for the different materials, from inconel to the simple stainless steel, from aluminum to the steel, aluminum to the titanium, aluminum to the copper, and other inert other ceramic materials also. So there are many more challenges in front of us to make the different kind of materials to be printed by using 3D printing or additive manufacturing. And one more conclusion for this FGM applications is medical implants, dental implants, aerospace and aeronautical applications, railway applications, defense, nuclear sector. You can see the video of powder bed fusion. This is a simulation for the powder bed fusion. So already we have seen in the we have worked on this powder bed fusion machine in NIT Warangal, worth of 3.5 crores, with a bed size of 500 mm. So you can see that video which represents the fusing of powder from bottom layer to the top layer. After every layer has been printed, that powder will deposit on the top surface of that object. So we are printing there in on bed, that is the multiple models, clones. We say as it's in 3D printing language, we say it as a clones. So that is the mode of printing. So we can remove that objects. So that is a metal powder. So after the printing, so we have to clean and remove that complete powder on that bed. We have to remove that turbine parts which are printed. So we can print. So this LMD laser metal deposition or direct energy deposition can be used to produce the multiple parts which are in turbine manufacturing used in aerospace as well as the aeronautical applications. And one more gradation is explained by the LMD in this video. So that is a powder. So he is setting the temperature as well as the frequency of power as well as the frequency of the deposition. Just like it's a fuse depositing machine. It's a bit of very costly, even though so in our Suzanne 3D Tech, we have started this to make easy for the direct energy deposition by using the wire arc method. So that is under the trial now. So we can able to produce the different material gradation for this aeronautical as well as aerospace applications. The next thing. So these are different types of aeronautical applications. That is the fuel pumps, fuel jets, as well as the turbine blades, exhaust ducts by using the lens technology. So recently, IIT Madras has been printed one exhaust duct, which is successfully launched in a satellite. As well as we can use in femur bone also. So in medical field, in medical prototyping, so we have to enhance the joint stability and reduce wear, cobalt alloy mating with the metallic part to reduce the wear rate. The porous titanium alloy mating with the bone to the enhance osseointegration and stability. So we have one more gradation. So in bottom figure, we are going to see, we are going to gradation from S1 to S5, as well as from R1 to the R3, and cobalt, chromium, the composition. That is, here we can say we are seeing that the 100% cobalt, chromium, molybdenum to 100% porous titanium TiC4 or TI6 TiAl4V structure for the reducing of wear. See, this is the part where the wear occurred. The utmost outer surface is cobalt chromium molybdenum liner, and the outer layer, so which is the wear resistant, that is a Ti6 aluminum 4V shell. So we can see here the gradation as well as the manufacturing lattice structure, that is the printing parameters, that is the porosity is 91% as well as is the strength of 1 GPa. So in this lattice, why? Because our whatever the joints in our bone, that bone structure is having the porous inside itself. So that porous can be manufactured with these cobalt, chromium, molybdenum, and this porous cellular structure utilized to reduce the stiffness as well as weight of the stem. So in conventional methods, there are solid metallic rods, that is titanium rods, or stainless steel rods, or steel structures are used in orthopedic as well as maxillofacial surgeries also. So now the research, this by the beauty of additive manufacturing as well as the functional gradation, so we can manufacture the more strength as well as less wear or wear resistance material can be produced by using the functionally gradation by using different metals. So we have plenty of challenges. So those are not the limitations, these are the challenges. Lack of comprehensive materials product manufacturing principles, guidelines, and standards for best FGM practices. Why? Because so if we go for the laser or direct energy deposition, still now we don't have the rules and regulations as well as the standards, just like ASTM. So we don't have that much ASTM standards while practicing this type of FGMs by using 3D printing. And one more, suitable methodologies have not to be yet to be established to fully enable to exploit the true potential of FGM on a commercial or economic scale. So this functionally graded additive manufacturing is still in research itself, and some of the parts, especially the in research institutes like IITs, NITs, and we the people also in our company, we are going to test this wire arc manufacturing, wire arc deposition modeling by using the simple deposition method. So these are all under construction mode itself. So that has to be enhanced towards to the commercial or economic purpose. And the next one, the AM systems have their restrictions on material selection. Besides, the uncertain behavior at the material interfaces has a significant influence on the quality of FGM objects. So if we unable to design the proper gradation between two material interfaces, so finally, ultimately that FGM printed material will be failed at any stage while it occurred, while it encounter with the temperature, exposed with the temperature, high temperature or cryogenic temperatures or high shock absorbing higher loads. So there will be a failure in between the material interfaces, and that has to be minimized by using the optimization of materials, optimization of printing parameters. So not many techniques has to be used for to get a proper FGM objects by using additive manufacturing. An intensive study to build a system with highly controllable process parameters to get desired performance and accuracy is needed. So here we'll get the machine learning models. Why? Because still now we don't have, so there is a limitation where still now we don't have the standards, proper standards and proper rules and regulation have uh, prepared and accumulated while designing and printing the 3D printed objects. So we have to go for the, so we can control the printing parameters. Minimum, we can print, we can control the printing parameters on board as well as before the printing also. So by using the accurate use of material as well as accurate use of printing parameters, that is density as well as the printing time as well as the layer which is going to be deposited. So these many printing parameters have to be properly designed in such a way that FGM should not fail. So thereby, so we can utilize this artificial intelligence, machine learning models to get the accurate as well as precise dimension as well as precise control parameters or process parameters to be used in printing. So therefore, I'm using this artificial intelligence in AIM process. So in AIM process, we have additive manufacturing with the machine learning or artificial intelligence, both the way we can call it. So that is in terms of material selection, material structure, that is a material design, as well as the material. You can see need of mechanical properties in material selection. If we want more flexible or more rigid, so whatever it may be. So this is just like a mm, optional thing we are going to program by using Python, as well as in material structure, as well as in material properties too. So in one case, we can see if we want to go for the best, if we want to out, you can say that the better mechanical properties are our outcome. So what are the predictions to be made for the input parameters? or input printing parameters. So for that, we can use the machine regression learning method. So in that, we have started with the data visualization as well as analysis, data processing, regression models, selection of best model, data prediction, and validation. So data visualization analysis, we can go for the data analysis processes, just like we can use the SQL as well as the Power BI, as well as the data processing, means data cleaning. So we can modify that data or filter the data. So this refined data should be produced. What the data, for example, we are going to print a square block of 20 mm with the PLA. So PLA characteristics are 180 to 200 degrees Celsius is the printing or melting temperature. So we have to judge what is the optimal printing temperature, 180, 190, 200 or 210. And another parameter, the bed temperature. For ABS, bed temperature will be 90 degrees Celsius. For PLA, that will be 60 to 70 itself. So we can print the PLA as faster rather than the ABS material. Why? Because ABS melting point is ABS printing point is printing temperature is the 240 to 270 degrees Celsius. On the other hand, the PLA have only 180 degrees Celsius. We can print the one from we can print the PLA in the FDM from 180 itself. So the speed of doing with the PLA is very easy. So we cannot go for much more speeder printing by using nylon or ABS materials. So these are some of the printing parameters. So for that printing parameters, the material output will be according to the time, according to the strength. So we have to collect that data in terms of output, say for the tensile strength. Okay. So for PLA or PLA composites, say compare the strength, mechanical strength from PLA to the PLA composite or PLA carbon composite, or ABS to the ABS carbon composite, nylon to the carbon composite. On the other hand, also the ceramics, zirconium, cobalt. Just we have seen in the femur example, the orthopedic surgeries, as well as the aerospace as well as the aeronautical applications. That is the titanium grade materials to the stainless steel materials. So we have to create or get the data from the experiment results or research details. So by using those data sets, we can form one one set of data towards the output of our model by using these regression models. So basically, I've used in my research, I've used this linear regression, random forest regression, support vector regression, gradient boost regression. So these are there are at most 12 models are there. So these 4 models are very you can see. So in my research, of course, based upon the model, based upon the data, so that model will be differ from person to person. But I've got the good prediction results by using these linear regression, random forest regression, support SPM, as well as the gradient boost regression. So for that, we can predict the results as well as the validate those results. Or suppose for the PLA, we are getting 40 MPa tensile strength. For PLA carbon composites, we are getting 70 MPa, for example. Okay, so validation. So we can simulate by using these regression models to validate that PLA, alone PLA tensile strength would be 40 MPa, as well as the composite PLA carbon composite maybe with the 70 MPa. So we can compare the data as well as classify the data, as well as whether our data is, we can also by using one more beauty also is there by using machine learning method, whether the data we have provided to the models is also, we can recognize that data is whether it is correct or not. It seems. So we can, based upon that data as well as the, based upon the regression methods, we can get the output by using data prediction as well as the validation based upon our output. And one more, this is the significance in AI in our manufacturing, that is, so we can reduce the cost. So as we have seen in the 3D printing, the same, so we can reduce the cost, we can reduce the material, we can reduce this time, as well as in FGM also. We can improve the strength. We can able to use multi-material. There is a multi-material choice in gradation. Likewise, so in artificial intelligence also, we have plenty of advantages that is used in supply chain, enhanced product quality, customization and personalization, data-driven decision making properly, competitive advantages, as well as safety and compliance, improved efficiency in terms of material, as well as manpower, as well as the investment for the final product output. So these are the advanced use cases of AI in manufacturing. These are the companies now have been used this AI for manufacturing. That is Samsung, ABB, Toyota, Haier, and Wipro. And we also see the Wipro 3D as well as Imaginarium in Pune also. They are using artificial intelligence. They have started now artificial intelligence in the direct energy deposition modeling. You can explore there. So these are the references. Thank you. Thank you, sir.
Thank you so much, sir, for the wonderful presentation. I request the participants, please unmute yourself and you can ask the doubts that you have. Or you can use the chat box also to post the questions.
Yes, yes, yes. So you can also contact me for different AM processes. So I can provide the different gradation also, as well as the direct energy deposition, which have been now it is under construction. So in very soon, we are going to get the now we are working on stainless steel as well as aluminum alloys. So you can go ahead.
Dear
With your
participants, any questions? Please unmute yourself and you can ask. Sir will clarify the doubts.
So most of them are familiar with these things, but as a industrialist, I can provide the different models as well as the especially for your MHRD projects. So for that, I can help.
Thank you so much, sir. Kranthi Kumar, sir. Thank you very much for the presentation and the insights given regarding the functionally graded additive manufacturing process. If any questions are there from the audience, I will ask them to post to you, sir, directly.
Sure, sir. Sure, sir. Sure, sir. It's a pleasure.
Thank you. Thank you so much, sir.
Thank you.